So I want to give some background on the plasma pickup transducing element, which is a humble gas discharge tube. By far the most common gas discharge tubes are the neon glow lamps, such as this one, which are still being manufactured. Primary usage is as indicator lights in like extension cords like this one. So inside here you actually have a guide just like this one over here. They can be operated both AC mains voltage, and in this case this is a DC power supply. So you see that we have 142 volts, 14.2 decavolts across the discharge, and there's also a ballast resistor in series to limit the current through the discharge. So in this case it's pulling 0.42 milliamps through the gas discharge tube. So yeah, these guys used to be more common. This is the General Electric glow lamp manual from 1966. The reason why we need that ballast resistor is if you look at the current voltage characteristic of gas discharges, the range here is from 10 to the minus 20 amps to 10 to the 2 amps. The voltage range is from 0 to 70 volts. Sort of normally what we expect is that the graph would be increasing monotonically. If you apply more voltage, you get more current. That is not always the case for gas discharges. There's like two regions here, two parts of the parameter space, where we have negative differential resistance. So that means that current actually increases when we drop the voltage. So this first region here is known as the subnormal regime of a glow discharge. Same thing happens again here. You have a negative slope, and this is an arc discharge. So this is something you want to avoid for gas discharge tubes. That's why you need to limit the current, typically with a ballast resistor, so you don't end up in an arc discharge, because that will pretty quickly destroy a gas discharge tube. But hence you always see the use of some form of current limiting, typically a ballast resistor like this one, and canonical values are like 100 or a few hundred kilo ohms. This is a slightly larger neon glow lamp. This model is called NE2. That's a General Electric designation for these guys. They were the original manufacturer. As you can see, the construction is very simple. This is a glass tube, 1/4 inch diameter, with 2 parallel electrodes. And inside the tube you have rarefied neon with a little bit of argon. The pressure is about 100 times less than atmospheric pressure. Alright, so the NE2 is connected, and in this case we actually have an adjustable ballast resistor, so we can kind of investigate different operating points. This current voltage characteristic is a measurement I made a couple of years ago for this very type of gas discharge tube, the NE2 neon glow lamp. So when you increase the voltage, you need to get up to the breakdown voltage, which is when you will see like a visible glow. There you go, boom. So it happened at about 80 volts. Here the current is pretty low, it's only 70 microamps. So you probably want to get a little bit higher to be in a more stable part of the operating regime. So we're going to crank this up half. And that's about as high as we can go here. So now we're operating this at 0.7 milliamps, which puts us right around here on the curve, which is, you know, pretty good operating point. So some very basic plasma physics tells us that the discharge current, 0.70 milliamps in this case, depend on the resistivity between the electrodes, which is directly proportional to the gas pressure. So at some point I got curious and said, hey, what happens if we excite the sound wave between the electrodes, in this case with the tuning fork. Shouldn't we be able to measure the current fluctuation caused by the pressure perturbation of the sound wave, which then directly changes the electrical resistivity? So the way it should work is that when you have a positive pressure perturbation, the electrical resistivity will go up, and then we should see a negative current perturbation. Of course, it will be by a very small amount, but I just got curious, would it be possible to extract this transduced signal? And it turns out with a bit of work, it is. So as soon as I had convinced myself that gas discharge tubes should make pretty good transducers, I sort of assumed that clearly this must have been done before. So I read a lot of scientific literatures and a lot of old patents. I didn't find anything, and then I found this GE manual. That should be like the authoritative document on all possible applications. I have a long list here. They mentioned relaxation oscillators, which is kind of neat. You actually take advantage of this unstable part of the operating regime, again where you have negative differential resistance that tends to drive instability and oscillations. So you could actually use a glow discharge tube operating in that part of the parameter space to drive a relaxation oscillator. So these were used especially in cars, both for turn signals and windshield wipers until not too long ago. You'd be surprised. Now I think it's completely replaced by semiconductors, by chips. This one is a neat one. Logic and computer applications, who knew? General glow lamp applications, voltage regulator, blah blah blah, stuff like that. But yeah, to my astonishment, there is no mention here of transduction. So it seems that this is actually a novel application I'm proposing here. Even this very simple NE2 25-cent neon glow lamp should have a pretty impressive frequency response. There are no resonances in the ultrasonic regime at least, and you should be able to go to very high frequencies. If you calculate the speed of sound and so on and so forth, compare with the electrode spacing, electron diameter, and things like that. So it might make a really good transducer of ultrasound propagating in solids and fluids are technical applications for this. So I've been doing quite a bit of work in this area, and compared to the sort of typical piezoelectric transducers, this is just a piece of piezoelectric crystal on a brass disc. These have resonances, typically tens of kilohertz or something like that, that kind of distorts the signal. They also don't particularly like heat. And one of the applications I looked at for the nuclear industry, they really don't like neutron flux. So it turns out that these gas discharge tubes are really robust. They can handle a lot of abuse. This guy has been encased in wet concrete. That cured. It has been heated to, it operated, this brave fellow operated for 100 hours at 400 degrees Celsius. And it still worked at the end of that, but then after it had cooled off, when I tried to power it up again, it ultimately failed. I think probably some air leaked into the tube. That's why it doesn't work anymore. But that's not really what this video is going to be about. That's going to be a separate video about technical applications. So what happened was that I was talking to people about this invention, and someone asked, "Hey, could you use this as a pickup for musical instruments?" And I said, "Sure, that should be trivial." And it turned out to be not completely trivial. I spent some time on it, but as we will soon demonstrate, yes, it does work. So the problem with this type of gas discharge tube for audible frequencies is that the pair of electrodes here might remind you of the tuning fork we just used. And unfortunately, they also act like a tuning fork. So in this case they have an eigenfrequency of about 1.4 kilohertz, which is right smack in the middle of the audible frequency range. So this particular tube is not suitable for audible frequencies. It works great for ultrasound, 20 kilohertz and above, and this guy actually has been working, I've shown it to work above a megahertz. So really good performer for high frequencies, but not for audible ones, because again you have some tuning fork action. That also brings me to another question I often get. People are saying like, hey, isn't this kind of like when you scream into a vacuum tube guitar amp? You can actually hear some transduction of your voice. And the normal transduction mechanism here is quite different. It's non-resonant. So yes, this resonance here at 1.4 kilohertz is an example of microphonics. But in our case, that is an undesirable effect. So we don't want microphonics. So we're not relying on them. We're actually very actively trying to avoid microphonics, which is a mechanical resonance of the structures inside the tube. So I did some digging to see what I could come up with. And I did find another type of gas discharge tube, which has mica support to keep the electrodes in place. So this guy turns out to be much better suited for audible frequencies. So let's fire it up and show what it looks like. Alright, so let's see if we can fire up this transducer candidate. 50, 70, 80, boom. Needed about 90 volts. And here you can actually see the semi-transparent mica support. Keeps the electrodes nicely in place. Suppress any eigenmodes and any microphonics here. So next we're gonna go and see if we can attach this as a pickup to a piano and try to record some music. Okay, this is going to be a tech demo where we will attempt to use a gas discharge tube as a pickup to record piano music. So here's our piano, and believe it or not, that is our plasma pickup. So this is the transducer. It's just a gas discharge tube. And here we have power supply consisting of 8 lead acid batteries. There is an audio transformer which is used to separate the signal from the DC discharge current. There is a preamp here, 2-stage preamp, 4 transistors, that is powered by its own 12-volt battery. And then we're just going to use an old phone to record the signal. So it looks like the phone is recognizing the plasma pickup as an external mic. So that's at least a good start. Alright, we're going to start recording. And I will just pick up the pickup. And I'm just gonna push it against the soundboard using my fingers, so it's not really ideal, but we'll see if it works. Alright, maestro, fire at will.